All right, let's jump right in. Today we're tackling a real classic from Irodov's problem book, number 1.115. So this one, it looks super familiar at first, right? A body sliding down a sphere. You've probably done that a dozen times. But it's got a twist, and I mean that literally. This sphere is spinning, and that one little detail changes everything. It turns a simple problem into a really cool test of our mechanics skills. You ready to dig in? Okay, so here's how we're going to tackle this. First, we'll really look at the problem and see what makes it so tricky. Then, we're going to jump into what's called the rotating frame. That's the key. From there, we'll figure out the exact point the body breaks away. After we've got that, we'll calculate the forces the problem asks for, and stick around to the end because I'm going to give you a simple checklist for any rotating system problem. All right, first up, let's really break down what we're up against here and understand the challenge before we even think about touching our calculators. So you read the first line, a small body starts sliding down a smooth sphere, and you think, I got this. It's a classic conservation of energy problem, right? But then you see that one little word, rotates. And that, my friends, is the game changer. It's not just a minor detail, no way. It's the absolute heart of the problem. If you miss that word, you're solving a completely different and much easier puzzle. So how do we even begin to deal with this rotation? Well, the smartest move is to change our perspective. Instead of watching from a fixed point on the ground, we're going to imagine we're right there, standing on the sphere as it spins. We're entering its rotating reference frame. And trust me, it's a whole new world in here. It's kind of like trying to play catch on a merry-go-round. The normal rules of physics seem, well, a little wonky. We need a new rulebook. And that brings us to this idea of a rotating reference frame. Now, the fancy term for this is a non-inertial frame. All that means is that it's an accelerating frame. You might think, wait, it's rotating at a constant speed, but remember, velocity is a vector. The direction is always changing, so it's always accelerating towards the center. Because of that acceleration, Newton's good old F equals ma doesn't quite work right. To make it work, we have to introduce a couple of what we call fictitious forces. Now, they're not fictitious like they're imaginary. They feel very real. They're just artifacts of us being in this spinning frame. Okay. Don't let this equation scare you. This is just Newton's second law, but for our new spinning world. On the left, we've got mass times acceleration, but it's the acceleration as we see it from on the sphere. On the right, we start with F. That's all the real forces we're used to, gravity, the normal force from the surface. But then we have to add our two new players, FCF, the centrifugal force, and FCOR, the Coriolis force. Those are our corrections that make the math work out perfectly in this rotating frame. Let's start with the centrifugal force, because you've definitely felt this one. It's that force that pins you to the outside wall of a spinning carnival ride. It's what feels like it's trying to fling you off a merry-go-round. It always points directly away from the axis of rotation. And its strength? Well, it depends on the mass of the object, how fast the thing is spinning, and how far you are from the center. All right, now for the Coriolis force. This one is a little weird. It's the one that trips a lot of people up. Here's the key. It only affects things that are already moving relative to the rotating frame. So if our little body was just sitting still on the sphere, there'd be no Coriolis force. But since it's sliding down, oh yeah, it's there. The best way to think about it is that merry-go-round again. If you try to roll a ball straight to your friend across from you, it won't go straight, it'll curve off to the side. That weird sideways push, that's the Coriolis force. Okay, so we've got our new set of rules and our new forces. Now we can get to the main event. Finding the exact moment our little body leaves the surface of the sphere. This is the real crux of the problem. So let me ask you this. Just take a second and think. Physically, what does it mean for the body to break off the sphere? In the language of forces, what happens at that exact instant? What force just disappears? You got it? The instant it breaks off is the instant the sphere stops touching it. It's no longer pushing up on the body. And what do we call that push? The normal force. So the critical condition, the key that unlocks this whole thing, is when the normal force N becomes 0. That's it. That's our golden ticket. N equals 0. Okay, so our goal is to find the angle where N becomes 0. But to do that, we first need to know how fast the body is going at any given angle. For that, we'll use the work-energy theorem. Basically, the work done on the body turns into its kinetic energy. Now, gravity is doing work for sure, but here is a super common mistake. A lot of students forget that in this rotating frame, the centrifugal force is also doing work. It's pushing the body outward as it slides down. You absolutely have to include that. Once we account for the work done by both gravity and the centrifugal force, we can get a nice, clean formula for the velocity. All right, step 2, we've got our velocity equation. Now let's look at the forces pointing in and out along the radius of the sphere. What do we have? We've got a piece of gravity pulling the body into the sphere, and we have two forces pushing out, the normal force from the surface and our new friend, the centrifugal force. All of these forces together provide the body's acceleration. And now, here's the magic moment. We take our golden ticket idea from before, and we set the normal force, n, equal to 0. We plug in the velocity equation we just found, rearrange the terms a little bit, and boom, out pops the angle we're looking for. And check this out. After we run through all that algebra, this is the result we land on. This is the expression for the cosine of our breakoff angle. See how it connects all the key variables? The acceleration due to gravity, the sphere's angular velocity, and its radius. It's all in there. This is a massive step. We've officially pinpointed that exact moment in space.
Okay, deep breath. We've done the heavy lifting. Seriously, the hardest part is over. We know the exact angle, which means we have a complete snapshot of the system right at that breakoff moment. Now it's just a matter of plugging and chugging. Let's calculate those forces. First up, the centripetal force. We know the formula. It's mass times omega squared times the perpendicular radius. And at our angle theta, that perpendicular radius is just r times sine of theta. We have m, we have omega, we have r, and we just figured out how to get theta. So this is just a calculator exercise now. So we punch in all the numbers from the problem, and we get 8 newtons. Perfect. That's our centripetal force. 1 down, 1 to go. All right, now for the Coriolis force. The formula, remember, is 2 times m times omega times the velocity v. And where do we get that velocity from? We go right back to that energy equation we built in step 1. We just need to plug in our special breakoff angle, solve for v, and we're good to go. We run those numbers, and we get our final answer, 17 newtons. And that's it. We did it. We've completely solved Irodov 1.115. We found both the centripetal and Coriolis forces right at that breakoff point. Awesome job. So yeah, the answers are 8 newtons and 17 newtons. But listen, the numbers are not the important part here. What's really important is the strategy, the thought process we used. Because this exact method will work for tons of other problems with rotating systems. So let's quickly recap our game plan. Think of this as your 4-step strategy for rotating systems. 1. Choose your frame wisely. 9 times out of 10, you want to be in the rotating frame. 2. As soon as you're in that frame, don't forget to add your fictitious forces, centrifugal and Coriolis. They're part of the deal. 3. This is the most important one. Identify the key physical event, like breaking off, and turn it into a simple math statement, like n equals 0. And 4. Don't be afraid to use all your tools. You'll almost always need a combination of both energy and force analysis to get to the end. All right, before we wrap up, here's a little something to chew on. What if the sphere wasn't smooth? What if there was friction? That's another real force we'd have to add. How would that change our work-energy equation? And what about our force balance? Where would you slot it into the strategy we just built? Think about it. Thanks for working through this one with me, and I'll see you for the next problem.